Okay, now we are getting into a little more complicated situation where we have two different samples. The good news is it's much more useful too. I mean, it's very common where you have two samples, one has one condition and one has the other, and then you compare them on something. So even though it is more difficult, stick with it here. So we have, in this case, a cold tablet, and there's some old version of the medicine and how long it took to recover, and some new tablet. And each of these numbers represents a patient and how long it took them to recover if they took this particular tablet. So just looking at these numbers, you can't really tell a lot about whether or not this new tablet is effective. We're doing a one-tailed test, which means we want to see, is this new tablet more effective than the old tablet? And if we send the data to Excel, which is what I would recommend, and remember all JMU students have free Microsoft Office. You can log in and get that software. So this is the old tablet and this is the new. So our first thought, if we're really trying to decide if this old tablet is less effective than the new, would be just to, let me put some lines under here. Let me get the average of these. So I'm going to type in equals and then average and then get everything there. And we can just copy that formula over here. Well, it's looking good from the first glance. The new tablet does have fewer days on average than the old one until people recover. The problem is this is just for our sample, and of course the marketers and the people taking this medicine want to know, is this true in general, not just for these 15 people or these 30 people. So somehow we have to find a way of figuring out if this is significantly less than this right here. And that's what we're going to be working on in this problem. So let's take a look. First of all, the null hypothesis. I think I've always said on your null, it should have an equal sign. So we want to stick with that, even with two-tailed test. And let's see how, okay, we're allowed to do a subscript here. So let's do subscript and we'll put mu. Whether we do mu1 or mu2 on the equal sign, it actually doesn't really matter. On our alternative hypothesis, it will matter because we're choosing a direction. But here, let's just put mu1, and then we'll do minus, do another one of these, mu2 equals 0. So what is this saying? This is saying null hypothesis is the nothing hypothesis, the boring hypothesis. If there's nothing going on, then the old medicine will be exactly as effective as the new medicine, and the average time to recovery for the old medicine will be exactly the same as the average time of the new medicine. So if that's true, if these two numbers are the same and we subtract them, we should get 0. That's what our null hypothesis is saying. It's another way you could write it is mu1 equals mu2. That would be perfectly fine way to say it. In fact, maybe that's, I'm going to change that because I think that makes our alternative a little easier to do. So let's do mu1 equals mu2. What I had before is correct, and that would be perfectly fine to have there. But this will make it a little nicer for our alternative. So our alternative, we know that there's going to be a sign change. We can't have an equal sign in our alternative. And we want to see if the mean recovery of mu1 is greater than the mean recovery of mu2. So we're going to put, let's see if it lets us do that. Same exact thing, except we want to see if mu1 is greater than mu2, which would mean the new medicine is better because we want a low recovery time, and u2 is our average recovery time for the new medicine. So we want that to be lower than this. So that's what the marketers of the new medicine, I'm sure, would want. If you had left mu1 minus mu2 equals 0 here, then here you would just have mu1 minus mu2 greater than 0. That would also be a correct alternative hypothesis. Okay, what should we use? We've only talked about z and t. Chi-squared and f are a little bit different. How do we know? Same as before. If we know the population standard deviation, we can use our z. If we don't, we use a t. Here, it tells us the population standard deviation for both of these. So because we have that, we can go ahead and use the z. And then the value of the test statistic. Okay, so this one's a little more of a bear here. Here is the formula. Let's see if I can. Okay, here's our formula, and we can do this in Excel or on a calculator. Let's see. Since we already did some in Excel, let's stick with Excel here. So I'm going to pull this over. And we have our sample means here. These are, maybe I'll just label them, sample means. So that's 1 and 2. Notice we need the sample variance. That's what this sigma squared is. Sigma is standard deviation. Sigma squared is variance. Luckily, that's pretty easy to get in a formula. You do the equals var dot and then s for sample, because you have sample variance. Hold on a second. Sorry, we have population, don't we? It's actually really rare in reality when you have the population standard deviation, but we do have sigma squared here. And I'm going to copy that formula over here for this data also. All right, so let's just set up this as one big formula here. Maybe I'll make this a little bigger. Maybe I will not make this bigger. Okay, anyway, we have our sample means, our sample variances. Let's just do the formula right here. So on the top, we're going to start by subtracting the sample means. So there's our x1 minus x2. And then we're going to subtract the two population means. These are the null hypothesis means. Well, we know that we're thinking this equals 0, or they're the same thing. If they're the same thing, then this is 0. So we can just put a 0 for this. And that will always be the case when you're doing two samples like this. And then we're going to put that entire thing in parentheses so that the entire top of our fraction is in parentheses here. Divide it by, and here we have a square root of, so we're going to get variance 1 divided by number of data points, and there's 15 there. You'll see that it's on row 16, but that's because row 1 has the column headers. So there's actually 16 data points there. And then I'm going to do the same with the second variance. What this is doing is just taking a weighted average of the two variances. And in this case, it didn't matter because they were both 15, so we could have just taken the direct average. And this gives us 0.9946. 0.994. Just double checking that. Yep. I could have just cut and paste that, I suppose. All right, p-value. So what's going on with p-value? Well, if we use our ALEKS calculator here, and we know that this is a z test statistic, 0.994. If we did the probability, let me just put this in and show you what happens. So this is the probability that our z would be less than or equal to 0.94, and we'd get a 0.839. That doesn't sound like a very good p-value, and in fact, it's not. Let me show you why something needs to be adjusted there. Okay, so if we think of our normal distribution here, there's our mean, and we have a z-value of 0.994. That's somewhere out here. Z equals 0.994. So what the calculator gives is everything to the left. And if our z-value was negative here, then the left would give us what's in the tail, which is exactly what we want. That's our p-value, the area out in our tail, just like for one sample test is our p-value. But here, we want the area in the tail. We want this area. So the p-value is always the area out in the tail, or tails if it's a two-tailed test. So that 0.839 that the calculator gave us right here, that's exactly the opposite of what we want. That's all this white area here. So if we subtract 1 minus that, 1 minus 1 minus that, that 0.839, I think it was, 8. I may not have rounded that completely. Let's see. 0.839. I may not have carried that out far enough. We'll hope for the best here. 0.161. That's our p-value, because that's the area that's in the tail. And because it's only a one tail, we're just doing a right-tailed test. We know that because this is a greater than sign, and I think they told us early on to do a one-tailed test. Because of that, we don't have to double this number. If this was a two-tailed test, we would now take that area in the tail and double it to account for both tails. So can we support the researcher's claim? In other words, are we able to reject the null? Well, our 0.05 level of significance is the bar that we were trying to get under with our p-value. P-value low, null must go. So if our p-value was below this 0.05, then we could reject the null and we'd say, hey, there is a significant difference. And in particular, the new medicine is lowering the average recovery time. But that's not the case here because our p-value is not below 0.05. So even though, this is important, even though our sample mean was about half a day less, the recovery time was about half a day less for this new medicine, that doesn't mean that we're confident that same difference would hold up in the population. Because our p-value is not below 0.05, it's questionable whether or not this same result would hold up in the population.